continuous function. So the definition is actually quite straightforward. Let's start with that. Yeah. So we have two topologies, x and y, and we have a function between them. So we have the sets and we have the function from one set to the other, and then we have their topologies, right? And we take any open set V of y, and if f inverse V is an open set in x, then the function is continuous. That's it. Yeah. Now, to check for continuity, it is sufficient to check whether the subbases are leading to a subbasis or just open. Is it open? Yeah, if the subbases are just the inverse image of subbases are open, that alone is enough to check for continuity because the the intersection of inverse images go inside, they can go in and out, and so can unions, right? We proved this in section 2. So because of that, yeah, we just since the finite intersections, which is what makes up the basis from the subbases, and arbitrary unions make the open set from the inverse images. From the subbasis, if we get an open inverse image, we're done. Just checking, is that it? Yeah. So yes, inverse image of. So if we just check that the inverse image of every subbasis element is open, we're done. Yeah. Okay, then it came the epsilon delta. Okay, I'll prove that right here. No, I'll prove it right after the coming term. So yeah, the examples are there. There's nothing for me to add, so I'm not going to say anything much. I will give the equivalence of the epsilon delta thing with the continuous definition right here itself. Yeah. So before that, I'll prove theorem 18.1. Yeah. So the following are equivalent. 1, 2, 3 first. F inverse U is open, aka continuity. F of A bar is contained in F of A whole bar, and F inverse B is open, closed for B closed in Y. Yeah. So let's prove that these three are equivalent first. Now, 1 implies 2. So, okay. Now let X belong to a closure, right? Now consider a neighborhood V of F of X. This must intersect F of A. This must intersect F of A since, hang on. Oh, we're not, yeah, sorry. I was getting ahead of myself. Yeah. Since X belongs to a closure, right? Yeah, so we have an arbitrary neighborhood V of F of X, right? And we have to show that V intersects F of A somewhere. Yeah, somewhere. We don't need a point other than F of X because we're not checking if it's a limit point. We're just checking if it's in the closure. Yeah. So F inverse V is open, right? So let's call it U. And U is a neighborhood of X, right? And U intersects A in some point. Can be X, doesn't matter. So let that point be Y, right? So U intersection A is contained, Y is contained in it, right? Now, because of this, F of Y is going to, well, lie in V and also in F of A, right? By the definition of F of A. So yeah, F of Y will always lie in F of A if Y is in A, which it is. So that means V intersection F of A is equal to F of, at least contains F of Y, right? And V was an arbitrary neighborhood. So if Fx is in a closure, then F of X is in F of a closure. So F of A, that's exactly what we have to show. So we're done. Now let's prove 2 implies 3. Okay. So let B be a closed set in Y, and F inverse B, let that equal A, right? So if we show that A is closed, we're done. So we have to show that A closure is contained in A, right? Okay. So yeah, F of A is equal to F of F inverse B. So it's contained in B for all functions, not it's contained in the case of surjectivity, I believe. Yeah. So now what? Hmm, am I going to cheat? I'll try now. Yeah. So if X belongs to A closure, right? Yeah. X will belongs to F of, so F of X belongs to F of A closure, which means it's a subset of F of A whole closure essentially, right? And that this is contained in B closure essentially, because F of A is contained in B, so F of A closure is contained in B closure, but B is closed, so it's equal to B, right? So that means F of X is uh, contained in B. So X is contained in F inverse, right? So we just showed X belongs to A closure implies X belongs to A, which is exactly this. So that proves 2 implies 3. And 3 implies 1 suggests a way of proving the equivalence between 1 and 3 without using 2 at all. So 2 is not necessary to show the equivalence. It's just used. In fact, I don't personally think 2 is a useful criteria at all. I think 1, 3, and 4 are the useful ones, but whatever. It's still a good exercise. So 3 implies 1 and is the same method for which you'd show 1 implies 3 directly. So yeah, F inverse U is equal to F inverse U is an open set in Y, right? Yeah. X, sorry, yeah, Y. Y minus B, where B is closed in Y, right? And this is equal to F inverse Y minus F inverse B. So remember that the minus just comes out for inverse images. It doesn't come out for the image sets. For that, we need injectivity. So F inverse Y will be the entirety of X because the image set of X is contained in Y. So the inverse image has to contain the entirety of X. So it's going to be X minus some closed set A. And the point is, since A is closed, this is open. So we're done. So yeah, these three are equivalent. Now, the important one, and this is what's going to be used to show the equivalence between epsilon delta and this. So 1 implies 4. Hang on, I'll just write 4 down. For every x in x, yeah, for all b of f of x, there exists u of x such that f of u is contained in, yeah. And the way to memorize this one is essentially this is like the epsilon delta definition. So V is the epsilon neighborhood. For all epsilon neighborhoods of f of x, there exists a delta neighborhood of x such that f of x is essentially f of x is contained in the epsilon neighborhood, right? So f of x under the delta neighborhood is contained in epsilon. So this epsilon is the neighborhood is decided by the epsilon, and we're just checking for that. And that's the way of memorizing it. And that's why that motivates the definition of continuity at a point x, right? So we're checking for epsilon deltas in one point. So yeah, how do we prove it? Let's see. So this one is supposed to be easier. Let's see. Yeah. So F inverse V is an open set, right? So okay, yeah. Fix an arbitrary point of x and take an arbitrary neighborhood V of x, F of x. Yeah. This is an open set U, and yeah, for all sets, f of u is contained in f of f inverse v. So sorry, this is equal to that, and this is contained in v. So f of u is contained in v, and we're directly done. What's harder is slightly harder is 4 implies 1, and that requires the basis trick we've been doing before. So 4 implies 1. Oh, I shouldn't have. But okay. So yeah, we want to show that f inverse v is right. So take any arbitrary x in v, right? Yeah, we had the, yeah, sorry. Mm, mm. Okay, f inverse v is a set, right? Yeah. So take any x in this, yeah, not in v. So take any x in f inverse v, right? Now, by 4, there exists ux such that, what? Let's see. Such that v is an open set and x is an arbitrary thing. Yeah, such that f of u x is contained in v, right? Should work out. I'll just check. I'm cheating a bit. Yeah. Mm-hmm. Okay, yeah. So f of x is in v. That follows directly. Oh, we had to be a neighborhood of x, right? We're using that side. Yeah. Yeah, I was a bit impatient. Okay. So v is a neighborhood of f of x, right? And because of that, we have a u of x such that f of u of x is contained in v. And now what? So yeah, u of x is therefore contained in f inverse v. This follows directly, right? Yeah, essentially, yeah. So u of x is going to be a superset. Hmm. Actually, yeah, let's see, it won't be u of x. Let's see. F inverse of f of u of x, ux is going to be contained in f inverse v. Hmm. Yeah, I'm confused. How is that possible? So this contains, oh wait, yeah, right. This contains u of x. So, yeah, my bad. This contains u of x by property proven in section. So this, therefore, by transitivity is the case. U of x is contained in f inverse v. So since we found a ux that's a subset of f inverse v for every x, if we take an arbitrary union x belongs to f inverse v, by the same trick of how we proved that T1 is equivalent to, that criteria, the non-containment one. By a similar trick, we can show that it's equal to an arbitrary union of open sets, and therefore is open. So that's how we show 4 implies 1. Okay, the definition of homeomorphism, that's also pretty simple. It's essentially an isomorphism, which essentially, in the context we've discussed, is sharing the same order type. Right? That's also called an isomorphism. There's also an isomorphism for algebra, so not getting into that. But essentially, if there's a topology preserving bijection, then it's a homeomorphism. And So if f is a continuous function from continuous bijective function from x to y, then yeah, since f inverse is also going to exist by bijectivity, if this also happens to be continuous, then it's a homeomorphism, right? So yeah, that's about it. And any no theorem to prove, I believe. Yeah, yeah. We'll deal with more in the exercises now. And yeah, if f of x is equal to z, z is going to be a subset of y, right? Yeah. So we have a continuous function, let's say x. We have a bijective function x from. Hang on, why would it be injective? We need an injective map, right? Yeah, we do need an injective map. Yeah. So we have an injective map from x to y, and BMH set this map. So we're changing the range here. Would be a bijective map, and it's a continuous bijective map. If f inverse happens to be continuous, then it's called an embedding from x to y. Yeah. Yeah. So I just remembered that I forgot the epsilon delta equivalence, but also realized that the hard part is actually behind us, since we proved 1 being equivalent to 4, and 4 is actually, I already showed why it's so similar to the epsilon delta definition. So we just have to show that it's equivalent to 4 actually, right? Okay, so 4 implies epsilon. Let's go this way. Yeah. So for all x belongs to x, that's there. For all epsilon greater than 0, right? There exists a delta greater than 0 such that what? Yeah, f of x. Uh, how is it written exam again? Yeah, um, x minus x naught less than delta, or in other words, x belongs to a neighborhood around x naught, since it is a neighborhood, or any open set containing x naught has a basis element which can be written in this form, implies f of x minus f of x naught is less than epsilon, right? Okay, so yeah, so 4 implies epsilon is quite easy. We just have for all v, right? So for all v, there exists a basis element, and the basis element would be determined by this epsilon. Why? Because yeah, so in any open set, you can always find a basis element, and in the standard topology, that basis element is going to be of the form. So we need a neighborhood of f of x, right? That's the criteria. I'll just check. Yeah, I think it is. I'll just check though. Yeah, every neighborhood of f of x. So it's going to be of the form f of x minus epsilon and f of x plus epsilon. That's the basis element. And so for all v, there exists epsilon greater than 0. So we are covering every epsilon, because essentially the v can go as small as we want. So every epsilon has to be touched upon, right? If you just consider the open intervals, with epsilon 1 by n, we consider every real number implicitly. So there's that. Now there exists the delta. So now we've essentially tackled every single v now, right? Are we proving epsilon implies 4 by accident? I hope not. Oh yeah, we are. We are. Okay. So yeah, this is an open set, right? Yeah. So this is a neighborhood v around delta, right? And a neighborhood around f of x. Sorry, f of x naught. Yeah. Now f of x lying in this neighborhood is the same as the statement. So just check that. To check that, well, yeah, it is exactly the same thing. if f of x lies here, then you can check that its difference must be less than epsilon. It's just is it a triangle? Hang on, it might be epsilon. Right? So yeah, take V to be this set, and then you'll get the epsilon thing here, right? Now, so we have so x naught minus delta and x naught plus delta is also an open set, and we yeah. So take U and take any basis element. That's going to determine our delta. And so that's how we obtain the delta, and that's how we get 4 implies epsilon. In either case, the book also has another proof. What's more interesting is epsilon implies, right? Yeah, that's where the V and the basis element come. So let yeah, let x fix an x belonging to x not belonging to x, fix neighborhood V of f of x, not right. Yeah. So now this thing has a basis element, right? So we can choose a basis element of V. So let's call it f of x naught. So whatever basis element you take, you can choose an epsilon such that it's a subset of that basis element, right? Okay. And we're given a delta less than we're given a delta neighborhood of x naught, and that also happens to be a neighborhood around x naught. So this is an open set including x naught, right? And f of x naught is f of x is in this neighborhood essentially by this epsilon delta condition. So in other words, f of u, this is u, and we found this u through the delta condition, and it's a subset of v, which is actually it's a subset of this set, which is a subset of v. It's a subset of the basis, which is a subset of. But yeah, so that's how we get epsilon implies 4. That's more interesting, and that's the main proof. This one also holds, but I'm essentially replicating what the book just checked. So yeah, another way of interpreting 4 implies epsilon is just taking it as the open set, which it is. But this is a far clearer visualization of the epsilon delta definition. Okay, so yeah, do I prove the continuity of that function? I don't want to. Okay, so any order preserving map is any order preserving bijection is a homeomorphism for between two order topologies. So I'm just going to directly prove that, right? Or I'm not going to. It's just quite easy. So let so f of AB is going to be a base an open set essentially, right? Why is that? That's because well, yeah, it's that's what it means to be order preserving. So if it's anything weirder, it wouldn't be order preserving, would it? So it has to be some open interval. And same thing with the inverse image, because the inverse image would be a since it's a bijective function, it will just essentially b equals to a comma b. So f inverse of c comma d would be equals to an open image too, an open interval as well. So because of that, and yeah, I remember that we just have to check continuity for the basis elements, not for anything else. So because of that, yeah, any such map is also a homeomorphism. And observe that both of these maps are actually order preserving bijections, except they're order preserving bijections from R to R, right? So example 4 is continuous. You don't really need calculus to show that they're continuous. But yeah, you can use the epsilon delta definition. That also works. For that, I am not sorry. Same thing with example 5, and yeah, example 6 is not continuous, or it is in one direction. Hang on, is it? Oh yeah, it's continuous in one direction. Yeah. So yeah, it's nothing much. It's just not continuous in the other direction because of this. It's leading to a non-open set. So yeah. Yeah, so where were we? Yeah, let's construct continuous functions from other continuous functions. Okay. Yeah. Okay, so the constant function is continuous because, well, let's see. Yeah. So let's say f is from x to y, and f of x is equal to y naught belonging to y. Yeah. So the inverse image of singleton y naught, right, is equal to the inverse image of y, right, or any open set containing y or anything, right? There are only these two sets to consider essentially, and either way you'll get x in all cases, and x is an open or closed set. So however you look at it, open and closed set. So that's why the constant function is always continuous. So yeah, okay. If A is a subspace of X, then the inclusion function J from A to X is continuous. So that's pretty simple too. Let's take any open set U of X, not neighborhood open set. So J inverse of U is going to equal to J inverse of U intersection A, because we're only considering so the inclusion function is essentially the identity function, but yeah, it's only defined for all points in A. It's not defined outside of A. So what does that mean? That means, yeah, we have to consider all the points in, right? And this, yeah, so I just said it's the identity function when considering points of A, right? So that means it's equal to U intersection A. But this is an open set in the subspace topology, so we're done. Composites. Yeah, composites are pretty easy. Let's see. So GOF, G and F are both continuous functions. Is it from, yeah, X to Z? F is from X to Y, and yeah, G is from Y to Z. Yeah. Okay, so let's take an open set in Z. Let's take U. G inverse of U is going to be what? An open set V of Y, right? It's an open set, and by continuity of F, the F inverse of G inverse of U is going to be equal to F inverse of V is also an open set W, right? And this is precisely the so why can we do it? Why are we free to invert like that? So why is this equal to essentially GOF inverse? I think we proved it in section 2. I'm going to check. After, yeah. Yeah, we did prove it. Yeah. So question 4A. Yeah. So I did it then. I have no idea what I did then. It's probably something, but I don't care. Either way, this and these are the same, right? Yeah. So the inverse image of an open set is an open. Okay, restricting the domain, so it's pretty similar to the inclusion one. Let's see. So yeah, okay. Is it an open set or any set? Subspace, yeah. Okay, restricting the domain, right. Uh-huh. So F is, oh yeah, it's just the composition of two continuous functions, right? Yeah. Yeah, so essentially this is equal to J composed on, so F composed on J, right? Yeah. So J goes from A to X to Y. So we have two continuous functions composed, and that's why it's continuous. Yeah. I know it's in front of me, but I'm trying not to cheat. I haven't cheated so far. Okay, Z is a subspace of Y containing the image set, then the function X to Z is obtained by restricting the range of F is continuous. Okay, so we're just restricting the range so that it's still containing the image set, right? So, mm, is Z a subspace? Yeah, Z is a subspace. Okay. Yeah, so because it's a subspace, any open set U of what? Yeah, so any open set U of Y, right? And that's going to correspond to an open set U intersection Z of Z, right? And the inverse image of U of Y is going to be the same as the inverse image of U intersection Z by, I think we proved it in inclusion, right? Yeah, similar to the proof of inclusion. Is it? No. Yeah, it is almost. Yeah. Hmm. Yeah, so any other point of Y is just going to return the empty set. So yeah, because if it's lying in view but not in Z, it's just going to be return the empty set, so we can safely union it and get the same set. So yeah, and because of that, the inverse images are equal, and therefore the openness remains as well, right? Now expanding, yeah. For expanding, same thing. We can union an extra part, and that extra part would be yeah, that is a space having Y as a subspace. Yeah. So we're just expanding essentially what are we expanding here? Also the empty set. So we're adding the empty set to it, so it doesn't matter. Local formulation of continuity. Yeah. So yeah, this I cheated on in the sense that I saw it before writing it down. So X is equal to union U alpha. Hmm. And let V be an open set. So F is going from U alpha to is it Y? Yeah, Y. Yeah. So yeah, F restricted to U alpha. Okay, so I'm just okay. This is actually F restricted to U alpha. I was calling it F alpha, but fine. Now this set, so yeah, V intersection. Yeah, so V. Okay, F inverse V. Yeah, sorry, I took a huge break. I saw some exercises. The break was well kind of predetermined, but yeah, a lot of stuff happened. Oh well. So yeah, I think I left it at restriction or expanding the range, right? Yeah. So let f of x till y be continuous, and yeah, z is a subspace of y such that it contains f of x. And okay, so we have a subspace, and we have to show that f this new f prime determined from f x to z is also continuous, right? So let U be an open set in Z, so it's equal to U intersection, let V be an open set equal to U intersection Y by Z, right? Now, yeah, so F inverse, F prime inverse V is equal to, hang on, yeah, F inverse V is equal to phi prime, yeah. F inverse U intersection Z, right? They're the same thing. And Z is it given to be an open set? I don't think you need it, but let's just check. Yeah. Okay. Uh-huh. Oh wait, F inverse Z is containing. So F of X is contained in Z, so F inverse of Z is containing X, right? Yeah. The inverse images carry over the containment. So that means we get, and the intersection comes out. So we have F inverse U intersection X, which is equal to F inverse U. So this is an open set, right? Since by continuity of F, it's an open set. So yeah, we can expand the range. And for restricting the domain, we just compose the inclusion function. So there we have it. Yeah, local formulation of continuity. So let X equal union alpha U alpha and F alpha, is it alpha or what? Yeah. Okay. F going from X to Y is continuous if F restricted to U alpha is continuous. Yeah. If every such thing is continuous. Yeah. And X is written as U alpha for such a case. Okay. So let V be an open set of Y. Right. Now F inverse V is equal to union of what? Okay, so this is equal to F inverse V intersection X, right? And this is equal to F inverse V intersection union of U alpha, right? Okay, and this is equal to F inverse. So can the union come out? Yes, it can by a distributive property of intersection. So let's write that down. Yeah, this is equal to union of F inverse V intersection U alpha, right? So this is an open set, this is an open set. So are we done? Yeah, I think we're done. Hmm. So this, oh, hang on. Yeah, this is okay. We're just this. If we assume this is an open set, it's circular, so we're not done yet. This is equal to U of alpha. But the good news is the U alpha is what? It's an open set in X, right? So, hmm, I'm cheating. Uh-huh. Okay. Oh, okay. Is it? Yeah. Let's see. So, right. This is precisely equal to F restricted to U alpha inverse image V. Right. And this is open by assumption. Yeah. So yeah, that's how you show a local formulation of continuity, and an extension, a similar extension for closed sets is called the pacing lemma. So it's I don't know why it's given a separate name. It really shouldn't be, but it is. So if A and B are closed sets, and in A intersection B, hang on. So A and B are closed sets, and there exists a function f and g from A to Y and B to Y, and in A intersection B, f of x is equal to g of x. Then then what? There exists an H from A, yeah, union B to Y such that H is continuous. Is that it? Yep. Okay. So it's pretty easy to show that. You just take an inverse image in any closed set in Y. Its inverse image will be F inverse C union G inverse C, and that's closed. Is that it? Yeah, that's it. And yeah, by continuity, it remains closed by theorem whatever. And finite unions of closed sets is closed, so we're done. And that's why the pacing lemma can be extended to essentially a finite collection of sets. To make sure that happens, let's see. So how do we use the, yeah. So we need to make sure that they're equal so that their union makes, yeah, we need to make sure they're equal so that the union makes sense. Otherwise, it won't be a rule of assignment. So yeah, that's where this hypothesis comes in. So there definitely exists a rule of assignment from A union B to Y. We just need these two to be continuous and closed and finite for the continuity. Yeah. Okay, maps into products. Show that. Were the exercises interesting? I'll just check. Yeah, nothing you haven't seen in high school. Yeah. Okay. Let A goes. Yeah. F is going from A to X cross Y, and F of A can be written as F1 of A, comma F2 of A. That's no problem because there's a bijective correspondence at the very least. So there's no problem that way. And we're showing that we have to show that F is continuous if and only if F1 and F2 are continuous. Yeah. So which direction should we go for first? Let's just choose one at random. Yeah. If F is continuous, then yeah. So I'll just show F1 is continuous and the other one is following from generality. So yeah. So note that these are functions from A to X and A to Y, right? So take any open set U of X, and by continuity, U cross Y is an open set. So F inverse U cross Y is equal to what? Some set in A, right? Now F1, so it's going to be an open set in A, and yeah. Now observe that since F1 inverse of U cross Y naught for any Y naught is going to equal to F1 F1 inverse U. Sorry, yeah, this is what I wanted to say. And why is that the case? That's because is it even true? Oh, sorry. Yeah, that's because this is actually F1 is equal to F composed on sorry pi 1 composed on F, and they're both continuous functions. But if you write it this way, then you can see that, and yeah, pi 1 is a continuous map because oh, did I not show it? Yeah, I haven't showed it. I'll show it now. I hope I haven't showed it. Whatever. So yeah, F pi 1 inverse of any open set U of X is going to equal U cross Y, since every Y naught can be used, right? So you have any X belonging to you, you can have any Y in Y, and they'll still give you the set U. So yeah, and similarly, any projection map is an open map. Actually, yeah, it's an open map, but it's also a continuous. Ah, that's what I showed. It was that it's open. Anyways, yeah. So this is a continuous function by composition actually. So one direction was a lot easier than I thought. Yeah. Now for the other direction, I think we're close. Okay, so we're given that it's continuous, and this is precisely equal to this because of this, right? Essentially what? Yeah, this is equal to, so I'm just flipping it around, right? Pi inverse, F inverse composed with pi inverse of U. And this is equal to U cross Y. So they're equal, right? Okay, now this is an open set. And therefore, that doesn't help at all. Sorry. Oh, right. So if we show that the basis elements are giving us an open image, then inverse image, then we're done, right? So this and x cross v, so this is an open set, this is an open set, and the intersection goes inside. So their intersection essentially, let's see. So these two intersected give rise to F inverse U cross V, right? So yeah, and this is a basis element. And this is an open set from this continuity. This is an open set from the other continuity, and therefore their intersection is also an open set because we're taking a finite intersection. Ah, that's why the product of both. Yeah, we're getting into that. Okay. So yes, that's how we show that the if and only if exists. Yeah. Actually, I probably won't prove the product topology continuity now because essentially, yeah, it just comes up into the pi inverse thing. And we're taking a finite union because that's how the product topology is defined. So yeah, we are quite close to that proof. Maybe I'll mention it. Okay, now what? Now we have is the exercises that yep, yep, the exercises. So yeah, also an update on the supplementary exercises. I have done till I'm in between question five now. So question two was the real hindrance. I have beaten that somehow, but so yeah, I should be able to complete it by at least section 22. So that's a good sign.